First data structure that we will talk about is binary search tree. In computer science, tree is made up from nodes, which contains some value, and edges. Since it is tree, we have something called root, and it is the node on the top. And in binary tree, every node can have left and right child. But this is not a rule. Nodes also can have only left or only right child, or they can have no child at all. For example, the right child of root have no left child. It have only right child. The nodes that have no childs are called leaves. Another word I will use is subtree. Subtree means every node in some part of a tree. For example, left subtree of root are all of these nodes, and right subtree of root are all of these nodes. Another important thing about binary search trees is that in the left subtree of every node are smaller elements, and on the right subtree of every node are bigger elements. So, for example, binary search tree can look like this. As you can see, subtree of root, every number is smaller than 28. And in the right subtree, every number is bigger. Let me show you how you can insert. Let's say we want to insert 2. We compare it to root, and since it is smaller, we know that it has to be in its left subtree. So we follow pointer to its left child. And we do the same here. So we compare 2 and 10. And since it is smaller, we go left. Now we compare 2 and 6. 2 is smaller, so we go left. But 6 have no child. So we set 2 as a left child of 6. That way, this tree will still be binary. Let's add 30. We start from root and we are comparing the number that we want to add with the node's value. If it is smaller, we go left. If it is bigger, we go right. We stop when there's no nodes to compare it. Then we set the value that we are adding as a child of node that we last compared. Let's do this. 30 is bigger than 28, so we go right. 30 is smaller than 36, so we go left. But there's no node, so we set 30 as a left child of 36. And we are done. Let me show you how the search works. Once again, we start from root. We compare the searched value to value of node. If it is smaller, we go left. If it is bigger, we go right. If it is equal, we found our element. And we do this until we find our element or until there is no child. When there is no child, searched value is not in the tree. Let's find 30. We start at root and go right. Then we go left and we found 30. Let's try to find 8. Once again, we start at root and go left. Since 8 is smaller than 10, we go left. Since 8 is bigger than 6, we go right, but 6 doesn't have a right child, so 8 is not in this tree. Let's try to delete some nodes. There are 3 cases that can happen. The simplest is that we want to delete a leaf node. We just found a node and delete it. For example, let's delete 30. So we search 30 in this tree and find out that it is a leaf. As I said before, we can just delete it because after deletion, we still have small numbers on left subtree and big ones in right subtree of every node. Second case is that the node we want to delete have one child. Let's try to delete 14. We find 14 and as you can see it have only right child. This is also pretty simple. We just set the pointer from the node that we want to delete to the only child. In this example, we set the right child of 10 to 18. The last case is that the node that we want to delete have 2 childs. Then we have choice. we can replace it with biggest number from left subtree, or we can replace it with smallest number from right subtree. But we are lazy programmers, so we just implement, let's say, biggest from left subtree. So, in this case, we replace the 28 with 18. Now, for every node is true that in its left subtree are smaller numbers and in its right subtree are bigger numbers. But sometimes can happen that the biggest number in left subtree or smallest number in right subtree have a child. Like in this example, I added left child to 18, but that is not a problem. We do the same. So we replace 28 with 18, and now we need to take care of that missing 18. And since it have only one child, we do the same as when we were deleting node with one child. So we set the right child of 10 to 12. And that's it. The time complexity of search, insertion, and deletion in average is big O of log n, because when we go to left subtree, we kinda get rid of right subtree. Other way to look at this is that we care about height of our tree, and the height is log of n in average case.